HighBridge, a division of Recorded Books, presents God and the Big Bang, 2nd edition, Discovering Harmony Between Science and Spirituality, by Daniel C. Matt, read by Barry Abrams. Preface. In the 20 years since I wrote the first edition of God and the Big Bang, there have been several significant discoveries in cosmology. Although none of these has compelled me to change any major themes or formulations in the book, I feel that it is worthwhile to revise some of what I have written in light of these new findings. One of the most significant scientific facts about our universe is that ever since the Big Bang, it has been expanding. As mentioned in Chapter 2, this was first demonstrated in 1929 by the astronomer Edwin Hubble. Until nearly the end of the 20th century, cosmologists assumed that the expansion of the universe was gradually slowing down due to the combined gravity of all the matter that exists. However, in 1997 and 1998, two independent scientific teams reported an astounding discovery. Based on their measurements of supernovas, spectacular exploding stars, they demonstrated that for the past several billion years, the expansion of the universe has actually been accelerating rather than decelerating. In recognition of their work, in 2011, both teams were awarded the Nobel Prize in Physics. What is causing this unexpected acceleration of the expansion of the universe? According to the most widely accepted hypothesis, it is a mysterious form of energy, a repulsive anti-gravitational force that cosmologists have labeled dark energy. Several billion years ago, as the density of matter and radiation dropped sufficiently, this dark energy began to dominate the density of the universe. The term dark energy resonates with the Kabbalistic term for the initial impulse of creation, Batzina de Cardenuta, a spark of darkness. The phrase dark energy is not really a physical description, but rather an admission of ignorance, a semantic surrender. This energy has never been directly observed, only inferred from astronomical observations. Over the past 15 years, two significant satellites were launched. First, the WMAP spacecraft, Wilkinson Microwave Anisotropy Probe, operated by NASA, and then the Planck spacecraft, operated by the European Space Agency. These have enabled scientists to determine that dark energy constitutes approximately 68% of the total mass or energy of the universe. Only 5% of this total is made up of ordinary atomic matter, constituting galaxies, stars, planets, and everything we can see and touch. Most of the rest, about 27%, is composed of another hypothetical substance, an exotic type of matter that does not interact with light and is therefore invisible. Like dark energy, this dark matter has never been directly observed, but only inferred, partly from its gravitational effects on ordinary visible matter. Yet even though we cannot observe this dark matter, billions of dark matter particles are passing through each of us every second. In other words, according to contemporary science, 95% of what exists in the universe is invisible and its nature unknown. We understand almost nothing about dark matter, and even less about dark energy. It seems that the more we know about the cosmos, the more mysterious it becomes. Does the Big Bang, which serves as the scientific creation myth of our culture, have anything to do with God? Can it enrich our lives? Physicists and theologians often contend that religion and science are two separate realms, each valid within its domain and operating under its own set of rules. The purpose of science is to explore nature, while the purpose of religion is to foster spirituality and ethics. But the question, how did the world come to be, is vital to both disciplines because it is so fundamental, a question that humans have pondered ever since consciousness evolved to a point where it could reflect on itself and the cosmos. This book opens with an account of creation according to the theory of the Big Bang. An overwhelming majority of cosmologists regard the Big Bang as the most reasonable explanation of the evolution of the universe, the best approximation to truth that we currently possess. But the name of this theory, the Big Bang, does not convey the awesome nature of the origin of the universe. Furthermore, it is misleading because it implies that matter and energy exploded like a giant firecracker or an immense nuclear bomb in the middle of empty space. Yet according to the theory, space itself is part of the expansion of the universe, and matter is just carried along by the expanding space. So the bomb analogy breaks down. There were no sound waves to make the bang audible. The expansion was smooth and continues to this day. The term Big Bang was coined by a bitter opponent of the theory, the English astronomer and physicist Fred Hoyle. In 1949, Hoyle gave a radio talk for the BBC on 20th century cosmology. Detesting the notion that the universe had a beginning, he held a different theory, according to which the universe is eternal. In his talk, Hoyle criticized the hypothesis that all the matter in the universe was created in one Big Bang at a particular time in the remote past. This Big Bang hypothesis is an irrational process that cannot be described in scientific terms. Although it is often claimed that Hoyle intended the phrase pejoratively, he denied this, insisting that he was simply seeking a striking image for the theory he opposed. In any case, the name gradually stuck. The origin of the cosmos has such grandeur, such an effect on our imaginations, that it has bestowed a measure of grandeur on the term Big Bang retroactively. Still, some scientists and science writers yearned for a different, more evocative name, so a popular astronomy magazine, Sky and Telescope, sponsored a contest to find one. Not one of the 13,000 entries impressed the esteemed panel of judges enough to warrant replacing Hoyle's phrase. Leaving the name aside, how does this contemporary creation story affect or challenge our concept of God? Can it help us discover a spiritual dimension in our lives and recover a sense of wonder? God and the Big Bang wrestles with these questions. In conceiving and formulating answers, I have drawn on the insights of traditional Jewish learning, especially the mystical traditions of Kabbalah and Hasidim, as well as contemporary physics and cosmology. I suggest several intriguing parallels, but my purpose is not to prove that 13th century Kabbalists knew what cosmologists are now discovering. Rather, in juxtaposing these two distinct approaches, the scientific and the spiritual, I experiment with seeing each in light of the other. I am not trying to synthesize the two, because their unique perspectives should not be collapsed. This book seeks rather to bring the two into dialogue. It is said that science demystifies nature, but scientists on the frontier are awed by the elegance and harmony of nature. As science reveals the secrets of the universe and deciphers the cosmic code, it evokes wonder. What science shows us about the evolution of our universe and ourselves is as awe-inspiring as the accounts in Genesis or the Kabbalah. Let me give two examples: the color of the sky and the force of gravity. Why is the sky blue? Among the wavelengths of light in the sun's spectrum, blue oscillates at the highest frequency and is therefore scattered effectively by molecules of air in our atmosphere. Because the blue light is bouncing off air in all directions, the sky turns blue. To me, this is more amazing than ancient Mesopotamian and biblical beliefs that the sky is blue because of all the water up there. Of the fundamental forces of nature, gravity is the one that most obviously affects our everyday experience. Gravity was conceived by Newton as a force exerted by objects in space, but Einstein showed us that it is a property of space, the curvature or warping of space-time. Imagine stepping on a trampoline. Your mass causes a depression in the stretchy fabric, and similarly with space. If you roll a ball past the warp at your feet, it curves toward your mass. The heavier you are, the more you bend space. As summed up by the physicist John Archibald Wheeler, space-time tells matter how to move. Matter tells space-time how to curve. On a cosmic scale, the force of gravity is now overpowered by dark energy, which is accelerating the expansion of the universe. However, our own galaxy is not expanding. It is simply being carried along by the overall expansion. So within our galaxy and solar system, and on our planet, gravity still wields its power unimpeded. Gravity is relatively weak between objects that have small masses, but it grows stronger as the objects grow in mass. So, something as large as the Earth exerts a mighty gravitational force. When you throw a ball up into the air, gravity quickly brings it back down to Earth, unless you're Superman, able to throw it at a speed of 25,000 miles an hour, fast enough that it can escape our planet's tenacious pull. As for the Earth, it is being drawn by gravity toward the massive Sun. Fortunately, our planet's forward motion and inertia counterbalance the Sun's gravitational attraction, keeping us in orbit around our star and preventing us from falling into its fires. The Sun, meanwhile, along with the whole solar system, orbits through our Milky Way galaxy and around the massive black hole at the center of the galaxy, and the entire Milky Way orbits with other galaxies in what is known as the local group, which itself feels the gravitational pull of the Virgo supercluster of galaxies. According to the law of gravity, every particle in the universe attracts every other particle, so every object in the universe feels the gravitational pull of all other objects, although the farther away an object is, the less its gravitational pull. Gravity is constantly trying to tug everything together, drawing each separate thing toward the original unity of the cosmic seed before it sprouted in the Big Bang. Gravity conveys a yearning for oneness. God is a name that we give to the oneness of it all. The theme of God as oneness is a recurring motif in this book. In Part 2, God, Self, and Cosmos, I explore the tension between this expansive view of God and the traditional personal God. I also discuss the link between the concept of a personal God and the notion of self. According to Kabbalah, the world exists and we have individual consciousness only because the infinite God has withdrawn itself from a single point of its infinity, thereby making room for finite being. We exist individually because we have lost oneness through a process the Kabbalists call the breaking of the vessels. Similarly, contemporary physics speaks of broken symmetry, through which the initial unified state of being shatters, eventually generating the diversity of galaxies, stars, planets, and life. Physicists search for the symmetry hidden within the tangle of everyday reality. They dream of finding equations that link the apparently distinct forces of nature. Spiritual search, too, in its own way, charts a course through multiplicity toward oneness. But is oneness livable? In Part 3, Torah and Wisdom, I outline a spiritual path that derives from Jewish tradition while remaining open to the wisdom of other faiths and the insights of science. I also touch on the problem of evil and describe the Jewish mystical technique of transforming the evil impulse. The book ends with a brief discussion of the fate of the universe and with reflections on our more immediate future. Where do we fit in the cosmic scheme of things? Earth, our precious little ball of rock 4.5 billion years old, circles the sun once a year. Our entire solar system revolves around the black hole at the core of the Milky Way galaxy once every 250 million years. Our sun is an inconspicuous star, one of at least 100 billion in our spiral galaxy. Our galaxy is one of at least 100 billion galaxies in the observable universe. Andromeda, our closest neighbor, lies 2 million light-years away. The two of us, Andromeda and the Milky Way, are members of the local group on the outskirts of the Virgo supercluster. Beyond lie so many clusters and superclusters that it takes volumes just to catalog them. They all appear to be arranged into gigantic domains that resemble the cells of a sponge. We are infinitesimal, yet part of something vast. Becoming aware of this, we strive to comprehend the entirety. On this quest, spirituality and science are two tools of understanding. Their approaches to the question of our origins are distinct and should not be confused. Each is valid in its domain. Occasionally, though, their insights resonate with each other. By sensing these resonances, our understanding deepens, nourished by mind and heart. Part 1. The Big Bang. 1. In the beginning. In the beginning was the Big Bang, 14 billion years ago. The primordial vacuum was devoid of matter, but not really empty. Rather, it was in a state of minimum energy, pregnant with potential, teeming with virtual particles. Through a quantum fluctuation, a sort of bubble in this vacuum, there emerged a hot, dense seed, much smaller than a proton, yet containing all the mass and energy of our universe. In far less than a trillionth of a second, this seed cooled and expanded wildly, faster than the speed of light, inflating into the size of a grapefruit. During this inflation, the potential mass and energy could not yet manifest as particles. Space was expanding too fast for any particles to congeal out of the vacuum. But as the expansion slowed down, energy latent in the vacuum precipitated as particles and antiparticles. These annihilated each other, except for 1 in a billion particles, which survived to become the building blocks of matter. The annihilation gave birth to a flood of energy, generating the radiation of the Big Bang. The ball of the universe continued expanding, and has never stopped. In its first few seconds, our universe was an undifferentiated soup of matter and radiation. It took a few minutes for things to cool down enough for protons and neutrons to form into the simple nuclei of heavy hydrogen and helium. But it was still far too hot for entire, stable atoms to hold together. Within about 10 minutes, the production of nuclei stopped. For the next several 100,000 years, the universe was somewhat like the interior of a star, filled with subatomic particles and photons, radiant particles of energy. In this early eon, the photons occupied a range of the electromagnetic spectrum beyond what the human eye can see. The radiation was so turbulent and energetic that electrons could not stick to nuclei to form full-fledged atoms. As soon as an atom began to form, it was immediately ripped apart by radiation. Frenzied photons collided with free electrons, traveling only an infinitesimal distance before the next collision absorbed or scattered them. Since no photon could escape, the mixture of radiation and particles was essentially opaque, like a thick, impenetrable fog. As the universe continued expanding, its temperature and energy gradually fell. After 400,000 years of cooling, when the temperature reached 3,000 degrees Kelvin, 4,940 degrees Fahrenheit, a transition occurred. Having lost a critical amount of energy, the photons could no longer tear away electrons from circling around nuclei. Relieved of the photons' constant harassment, the electrons were now free for the first time to settle into orbit around the nuclei, forming stable atoms of hydrogen and helium, which, millions of years later, would grow into stars. Meanwhile, with unattached electrons no longer available, the photons were also freed. able to travel great distances without colliding with an electron and being scattered or absorbed. The photons broke away from the building blocks of matter and became visible, flying through space in all directions. Matter and radiation had decoupled, and the universe turned transparent. This is the moment of "Let there be light," Yehi Or. The echo of the Big Bang. Ever since, for 14 billion years, radiation has pervaded space. As the universe expanded and cooled, the radiation's frequency continued decreasing below the visible and infrared ranges and into the microwave region. This cosmic background radiation is the residual heat signature of the Big Bang, its faint, persistent echo. In the late 1940s, the physicists Ralph Alpher and Robert Herman theorized that this echo was still circulating through the universe. But it was not until 1964 that it was discovered, by accident serendipitously, in New Jersey. Two radio astronomers, Arno Penzias and Robert Wilson, were scanning the heavens with a new 20-foot horn-shaped reflector antenna at Bell Telephone Laboratories in Holmdel, New Jersey. Whenever they turned the antenna, they picked up a mysterious background hiss. They first attributed this to electrical static caused by contaminants inside the horn antenna, maybe accumulated pigeon droppings. They dismantled and cleaned the throat of the antenna, but the static persisted. Meanwhile, in Princeton, about 25 miles west of Holmdel, the physicist Robert Dicke and his colleagues were designing an experiment to detect the cosmic residue of the Big Bang. Penzias heard about the Princeton work and contacted Dicke. Upon hearing of Penzias's and Wilson's discovery, Dicke turned to his colleagues and said, "Well, boys, we've been scooped." The puzzling hiss was indeed the cosmic background radiation, the echo of the Big Bang. Its temperature was close to what Alpher and Herman had predicted years earlier, about 3 degrees Kelvin above absolute zero. The cosmic background radiation offers us an image of the universe 400,000 years after the Big Bang, the last time radiation interacted with matter. In 1989, the Cosmic Background Explorer satellite, COBE, was launched to analyze the structure of the background radiation in microscopic detail. 3 years later, the COBE team announced that they had detected slight variations in the temperature of the radiation, the imprints of ancient ripples in the fabric of space-time. These variations, caused by slight differences in the density of the universe in different regions, reveal that matter was not uniformly distributed. Here and there, hydrogen and helium were already being tugged together by invisible dark matter, beginning to assume a structure that would evolve into galaxies and stars. The large-scale structures in the universe today, the clusters of thousands of galaxies, illuminate these ancient ripples like glitter tossed on invisible lines of glue. For eons, in areas of our universe that were slightly denser than average, gravitation had its effect, slowing down the expansion. Imagine a galaxy beginning to form. First, dark matter and ordinary matter, hydrogen and helium, form a halo. Within this halo, the hydrogen and helium cool further, falling toward the center. Gradually growing in density, these glimmering clouds of gas form into stars. Within each star, more helium is formed by the fusion of hydrogen, generating energy and fueling the star. After the core of the star has been mostly converted into helium, the star becomes a red giant and begins fusing helium into still heavier nuclei such as carbon, silicon, and oxygen, generating further energy. If the star is of medium size, more massive than our sun, after eventually turning into a red giant, it will blow off its outer layers to form a gas cloud called a planetary nebula. These nebulae scatter elements such as carbon, nitrogen, and oxygen into space. If the star is originally massive enough, at least 8 times as massive as our sun, it will eventually convert most of the material in its core into iron. Because iron has such a tightly bound nucleus, it becomes impossible to extract any energy from it by further nucleosynthesis. At this point, the massive star is doomed. The energy generated by fusion had supported the star's outer layers, countering the force of gravity. Without this support, the star collapses. As the entire mass of the star plunges toward its core, a burst of energy rebounds from the center as a huge shock wave. The star explodes, in the violent process forging even heavier elements, such as copper and silver. These, along with the lighter elements from the exploding core, are spewed into space. Other heavy elements, such as gold, platinum, and uranium, may be ejected from the merger of very compact stars known as neutron stars. Over eons, these various elements recycle themselves into new solar systems. Our solar system is one example of this recycling, a mix of matter produced by cycles of stars forming and exploding. We, along with our planet and everything on it, are literally made of stardust. Stirring the primordial soup. 10 billion years ABT, after the beginning of time, in a spiral galaxy called the Milky Way, about 2/3 of the way out from the galaxy's center, an immense cloud of gas and dust started to contract. The gas consisted of hydrogen and helium, the dust of interstellar particles such as carbon and silicon atoms. As the cloud collapsed toward its center, its rate of spin increased. This is similar to the spinning speed of a figure skater increasing as she pulls her arms inward. The centrifugal force of the spin flattened the cloud into a disk. Counter to this outward thrust, the attraction of gravity pulled most of the matter to the central region, eventually forming the sun. Within the flattening disk, particles not drawn into the center were able to cluster and cool into chunks of material, which in turn collided to form planets. Attracted by the gravity of the sun, each planet eventually settled into an orbit around the solar center, although the early solar system likely had episodes of major rearrangements. The planet we call Earth took shape and began cooling down about 4.5 billion years ago. By about 1 billion years later, various microorganisms had developed. Exactly how, no one knows. But we do know that Earth's early atmosphere was composed of hydrogen, water vapor, carbon dioxide, and simple gases such as ammonia and methane. In such a climate, organic compounds may have synthesized spontaneously. Scientists have replicated the Earth's infant atmosphere by blending molecules of its components and exposing the mixture to ultraviolet light, which was stronger when the Earth was young, and electric sparks, approximating the action of lightning. The result? Amino acids assembled themselves along with other organic molecules. Or perhaps life drifted to Earth in the form of spores from another solar system in our galaxy. However life began, all its forms share similar genetic codes and can be traced back to a common ancestor. All living beings are cousins. We humans like to think of ourselves as the pinnacle of creation, and it is true that we are the most complicated things that we know of in the universe. We are composed of about 10 trillion cells. The retina of the human eye alone contains 3 million cells, each connected to the brain by an individual wire in the cable of the optic nerve. Our brain contains 100 billion cells, linked by over 100 trillion synaptic connections. Yet, we are part of the evolutionary process, descended from single-cell organisms that lived 3.5 billion years ago. We have evolved through an intricate, unrepeatable combination of chance mutation and natural selection. Our species, Homo sapiens, developed in Africa, splitting away from the chimpanzee line about 7 million years ago. We still share with the chimps 98% of our active genes. If you'll pardon the expression, we are an improved ape. Before the Big Bang.
Sample complete. Ready to continue?